The story of the universe begins with something deceptively simple: a speed. In the early years of the 20th century, Albert Einstein declared that light, traveling through empty space, always moves at the same pace. No matter who measures it, no matter how fast they themselves are moving, the number remains unchanged. This cosmic constant is 299,792,458 meters per second. At first, it sounds like just a figure, another measurement in a world filled with countless ones. But behind it lies the foundation of modern physics, the principle that reshaped space, time, and reality itself. Einstein dared to imagine a universe where the speed of light was not just a useful measurement, but a universal boundary. Imagine a cosmic highway with lanes stretching forever. But every traveler, no matter how powerful their engine, runs into an impenetrable wall when they approach the velocity of light. Trains, rockets, particles, even thoughts carried by signals, all are bound by this upper speed. It is not negotiable. It is not conditional. It is the same in every frame of reference. Whether you are standing still on Earth, riding on a spacecraft, moving at thousands of kilometers per hour, or surfing on a beam of radiation from a distant galaxy, the number does not shift. This was Einstein's audacious claim, one that no experiment has ever refuted. The consequences ripple through the structure of the cosmos. If light is fixed, then time itself must bend. Distances must stretch or compress. Causality, the chain of events that dictates that causes led to effects, becomes guarded by this constant. Without it, paradoxes would unravel reality. A world where signals could move faster than light would allow messages to outrun their own senders, effects to appear before causes, histories to contradict themselves. The speed of light is not simply a number. It is the rhythm that keeps the universe logical and coherent. Consider daily life, invisible but quietly dependent on this principle. Your phone finds your location using signals from satellites orbiting thousands of kilometers above the planet. Those signals, racing at light speed, carry information about distance and timing. If the constancy of light were not reliable, your navigation would be impossible. Airplanes could not track routes, financial systems would desynchronize, and the infrastructure of the digital age would collapse. The cosmic speed limit is not only for physicists, it pulses through the technology we take for granted. Now expand the view outward. In the vast theater of the cosmos, light speed dictates how we see the stars. A galaxy 1 million light-years away is observed not as it is now, but as it was when that light first departed. 1 million years in the past. The night sky is a time machine, each photon a messenger preserving history. The fixed pace of light allows astronomers to reconstruct the timeline of the cosmos. When they look at quasars blazing at the edge of the visible universe, they are seeing echoes from when the universe was still in its infancy. The speed of light is the very reason the past is visible at all. This constancy also defines boundaries we cannot cross. Black holes, those collapsed stars of unimaginable density, mark the point of no return precisely because light cannot escape their grip. Once light itself is trapped, no information, no signal, no possibility of communication can emerge. The boundary is called the event horizon, a one-way veil. Beyond it, the universe keeps its secrets forever. Again, the unchanging pace of light makes the difference between what can be seen and what remains hidden. Even the grand expansion of the cosmos is told in terms of light speed. Galaxies are receding as space itself grows, and some already move away faster than light due to the expansion of space-time. Their signals will never reach us. There are parts of the universe we will never know, not because of technology, not because of distance alone, but because the cosmic speed limit forbids it. We live in a horizon of knowledge, bounded by light. Our cosmic story is told within that circle. Einstein's simple postulate has been tested in every way imaginable, from particle accelerators hurling protons to nearly light speed. to delicate observations of distant pulsars flashing with clock-like precision, the verdict is always the same. The constant holds. Even the tiniest deviations, if they exist, must be vanishingly small, far beneath the reach of current experiments. The cosmic speed limit is the most trustworthy law we know, a law that unites the microcosm of quantum particles with the vastness of galaxies. And yet, the mind stirs at the question, is this constancy absolute, woven into the very essence of reality, or is it a shadow of deeper truths? What if the vacuum, the stage upon which light travels, is not the pristine emptiness we imagine? What if emptiness itself conceals an underworld of activity, restless, seething, alive? Could light's perfect uniformity mask subtle tremors beneath, distortions so faint that only across billions of light years might they reveal themselves? The constant may not be as simple as it seems. What if the void itself conspires to make light stumble? What if the vacuum is not truly empty at all? Light is constant, yet our imagination is restless. Once Einstein revealed the unshakable speed limit of the cosmos, humanity began to wrestle with consequences that seemed almost fantastical. The twin paradox, for instance, is no science fiction trick, but a natural prediction of relativity. One twin remains on Earth, the other boards a spacecraft and approaches the velocity of light. When they reunite, the traveling twin has aged less. Time itself has bent differently for each, sculpted by motion. What once seemed like an immutable flow is instead elastic, stretching and compressing as speed approaches the universal boundary. This is the cost of the constant pace of light. Space and time are not rigid arenas, but flexible fabrics, their threads rearranged so that light always moves at the same tempo. In laboratories and observatories across the planet, this has been verified beyond doubt. Muons, subatomic particles born from cosmic rays striking Earth's atmosphere, should decay in a fraction of a microsecond. By all expectation, they should vanish long before reaching the ground. Yet they are routinely detected on the surface. Why? Because at near light speed, their internal clocks slow relative to ours. Time dilation gives them an extended lease of existence. The effect is not hypothetical. It is real, and it is a direct testament to the cosmic speed limit. The universe conspires to uphold it at every turn. The constancy of light speed is also the anchor of causality. Imagine sending a signal faster than light. In one reference frame, it might be received before it was even sent. A message could arrive before the decision to write it. A bullet could strike before the trigger was pulled. Events would scramble themselves into paradox. Relativity seals the universe against such disorder. The speed of light is not merely a maximum pace. It is the guardian of chronology, the principle that preserves the arrow of time. Without it, the very notion of past, present, and future would dissolve into contradiction. For everyday life, this cosmic speed limit hides in plain sight. It lurks inside the functioning of your GPS receiver, which requires measurements precise to billionths of a second. The signals from satellites would be nonsense if not corrected for relativistic effects. Engineers account for time dilation due to both the speed of the satellites and the weaker gravity they orbit in. Without those corrections, your car might be directed miles away from its true location. Light's constancy is not an abstract principle, but the hidden framework of modern civilization. Cinematic though it may sound, relativity transforms perception itself. A spacecraft accelerating to half the speed of light does not simply move faster. To observers inside, time feels normal, clocks tick steadily, conversations flow naturally. But to an outside observer, those clocks run slow. Distances in the direction of motion shrink. Energy required to accelerate grows ever larger, approaching infinity as speed approaches the limit. Thus, no machine, no clever trick of engineering can cheat this law. The speed of light is a fortress at the edge of possibility. In the cosmos, this fortress shapes everything we see. Supernova explosions send waves of light and particles across interstellar gulfs. That light carries the story of the explosion faithfully at the one permitted velocity. Radio waves sweep from pulsars, rotating neutron stars across light years of space, arriving on Earth with clock-like regularity. We rely on the constancy of their signals to test relativity and probe the structure of space-time. Light's uniformity is what turns the universe into a readable book. Without it, the pages would scatter, the words would blur, and cosmic history would be illegible. Still, even within the comfort of this constancy, questions remain. If the speed of light is always the same, what about the medium through which it travels? We call it vacuum, but is it truly nothing? When 19th century scientists imagined an ether filling space, Einstein demolished the idea by showing that light needs no medium. It is self-propagating, carrying its own electric and magnetic fields through emptiness. Yet quantum physics whispers that emptiness is not barren. The vacuum, far from being an empty canvas, may be alive with invisible fluctuations. Even in regions stripped of all matter and radiation, energy cannot be entirely zero. Heisenberg's uncertainty principle demands that at the tiniest scales, the vacuum quivers with restless motion. Could these unseen vibrations subtly affect the march of light? Einstein's postulate stands unbroken, yet every constant in science is also an invitation to challenge it. The deeper we peer, the more precise our measurements, the more we are tempted to wonder if cracks might emerge. The fabric of space-time may not be smooth and continuous at the smallest imaginable scales. It might froth, churn, and twist, producing a hidden turbulence through which light must pass. If so, then the absolute constancy we worship may be only an approximation, a grand illusion. To test such ideas requires not only courage, but instruments capable of probing the universe across unimaginable distances. In a sense, the cosmos itself provides the laboratory. Every photon from a distant star, every gamma ray from a cosmic explosion, is an experimental probe. As these particles of light traverse billions of years of space, any deviation from perfect constancy should accumulate. If light is slowed, scattered, or deflected by the invisible structure of the vacuum, then by the time it reaches Earth, the signals should betray the disturbance. The uniformity of arrival times, the crispness of pulses, the synchrony of photons across energies, all these become clues. So far, they have confirmed the law. But the deeper the search, the more profound the potential discovery. For if constancy breaks, our understanding of reality itself must be rewritten. And so, beneath the triumph of Einstein's vision, the question begins to haunt. If light moves through what we call empty space, but empty space itself is not empty, what then? Is the speed of light constant because the vacuum is perfectly smooth, or is constancy enforced despite a chaotic underworld we cannot yet perceive? Perhaps the vacuum is like the surface of the ocean seen from far above. From a distance it appears calm and flat, but up close it seethes with waves, eddies, and foam. Could space-time itself, at the smallest scales, resemble such a sea? And if so, what becomes of light as it tries to cross that frothing expanse? The thought of emptiness as smooth and featureless has comforted science for centuries. We imagine light gliding effortlessly through a pristine void, like a bird across still air. Yet the closer we look, the more this picture trembles. Relativity assures us that the speed of light is absolute, yet quantum mechanics hints that the stage it travels upon may be anything but still. To reconcile these visions is to walk the edge of mystery, balancing certainty against possibility, order against chaos. Imagine yourself standing in a vast desert at night. The sky overhead looks calm, serene, peppered with stars. To the eye, it seems eternal, silent, still. But if you could magnify your view far beyond what even the most powerful telescope allows, if you could dive into the very scaffolding of space-time itself, you might find a landscape that is anything but calm. Waves might surge, bubbles might burst, threads of geometry might twist and snap. This is what some physicists suspect awaits at the smallest conceivable scale, a scale known as the Planck length, a dimension so tiny that it makes the proton seem like a giant. At such scales, the neat constancy of light might be challenged, not by disobedience, but by the turbulence of the stage it crosses. Yet we cannot abandon the triumph of Einstein too quickly. The constancy of light has been tested across every experiment ever conceived. From atomic clocks ticking on mountainsides to spacecraft carrying signals across the solar system, the verdict never wavers. Light always travels at the same pace in vacuum, never faster, never slower. If there is turbulence beneath, it is buried under layers of apparent perfection, hidden so deep that only the universe itself, across billions of years and billions of light years, might amplify its whisper into something we could notice. The search is as much philosophy as physics, for it asks what we mean by emptiness and what it means for laws of nature to be absolute. Consider again the cosmic consequences of the speed limit. Every time we gaze at the night sky, we are not looking outward so much as backward. The light from the sun takes 8 minutes to reach Earth. The light from the nearest star requires over 4 years. Galaxies at the edge of what we can see send light that has traveled for more than 13 billion years. This constancy transforms the cosmos into a record of its own history, a record written in light. But if the vacuum is alive, if it writhes with unseen activity, then this record may be slightly distorted. Photons might be delayed, dispersed, or blurred, their once perfect uniformity scarred by a journey across space-time foam. Such speculation does not diminish Einstein's vision, it deepens it. For science advances not only by what is confirmed, but also by what resists confirmation. The speed of light, declared absolute in 1905, still holds its throne. Yet the possibility that it may conceal subtle variations drives entire fields of research. Observatories scan the skies for gamma-ray bursts, those titanic explosions in distant galaxies. Physicists analyze the timing of photons arriving from quasars and pulsars. Each observation is a test, each photon a question asked of the universe. The answers so far repeat the same refrain: light is constant. But repetition only heightens the suspense. If a crack appears, if a deviation is ever found, it will shake physics to its core. The tension between certainty and curiosity is the heartbeat of science. On the one hand, we rely on the constancy of light to uphold causality, to protect the logic of time. On the other, we wonder whether the universe at its most fundamental scale respects this law or merely approximates it. Are we like sailors who trust the calm sea while knowing that in its depths storms rage unseen? Or is the calm surface all there is, an unbroken tranquility? The answer matters, for it would reshape our understanding of not only light, but of space, time, and reality itself. And so the story pauses on the edge of revelation. We have seen how Einstein's postulate underpins relativity, how it secures causality, how it dictates the rhythm of the cosmos and governs both daily technology and the grandest structures in space. We have imagined its cosmic consequences, from black holes to expanding horizons. Yet a question lingers, like a whisper in the dark. If the speed of light is constant, what is the nature of the emptiness it travels through? Is it a void, pure and perfect, or a living ocean of unseen motion? If the vacuum is alive, then perhaps constancy is not the whole story. Perhaps light is not gliding effortlessly after all. Perhaps it is struggling ever so slightly against a sea of foam. The idea of emptiness is ancient, rooted in philosophy as much as science. For centuries, thinkers argued whether nothingness could even exist. Was space a stage upon which matter performed, or was it an illusion conjured by the presence of things? When physics matured into its modern form, it seemed the question had finally been answered. The vacuum, stripped of all air, all particles, all fields, was pure nothing. Into this nothing light could race unimpeded, upholding Einstein's great postulate. But the 20th century, with its quantum revolutions, shattered this calm image. Emptiness, it turned out, was not truly empty. the vacuum was alive. Quantum field theory, the framework uniting quantum mechanics with special relativity, paints a picture of reality that is startling in its implications. Every particle is not simply an object, but an excitation of a field. Electrons arise from the electron field, photons from the electromagnetic field, quarks from their own fields. These fields extend through all of space, present everywhere at every moment. Even when no particle is present, the field remains, and it is never truly at rest. Emptiness is revealed as a restless sea, vibrating with potential, crackling with invisible activity. This is the quantum vacuum, a place where virtual particles flicker into existence only to annihilate an instant later, a constant dance permitted by the uncertainty principle. The Heisenberg uncertainty principle, so often misunderstood as a vague statement about measurement, is in truth a precise rule about nature's limits. It declares that certain pairs of quantities cannot both be known with arbitrary precision. Position and momentum, energy and time, each pair is linked in a fundamental trade. This trade is what fuels the vacuum's vitality. If energy and time cannot be pinned down absolutely, then energy can briefly appear out of nothing, provided it vanishes quickly enough. Like actors stepping briefly onto a stage before retreating into the wings, particles and antiparticles emerge from the void, borrow existence, and dissolve back. Though fleeting, their presence has measurable consequences, rippling through the observable universe. One of the most famous examples is the Casimir effect. Place two metal plates very close together in vacuum, separated by only a hair's breadth, and a force will push them together. This force does not arise from any conventional source. It is the pressure of vacuum fluctuations, the imbalance of virtual particles inside the gap compared to outside. Empty space, far from being void, exerts a tangible influence. It is as though the vacuum itself insists on reminding us that it is alive, humming with activity even when stripped of matter and radiation. This effect, small but undeniable, is a window into the restless heart of nothingness. In cosmology, the vacuum's vitality becomes even more staggering. The expansion of the universe is accelerating, driven by what we call dark energy. Its nature remains mysterious, but one candidate is the energy of the vacuum itself, the sum of all those restless fluctuations. If true, then the fate of the cosmos is being dictated by the vitality of emptiness. Galaxies will be torn farther and farther apart, horizons will retreat, the night sky will grow lonely, all because of energy hiding in the vacuum. Nothingness, far from powerless, holds dominion over the largest scales of existence. This picture challenges the comforting simplicity of Einstein's postulate. Light travels at a constant speed through vacuum, but the vacuum itself is a medium alive with unseen motion. Does this seething activity affect the march of photons? Do the flickering virtual particles, the restless fields, alter the constancy of the cosmic speed limit, if only by the smallest margin? For the most part, the answer appears to be no. Careful experiments find light unwavering. Yet the possibility that fluctuations might, at the tiniest scales, nudge its path remains a tantalizing speculation. The search for such effects drives entire branches of theoretical and experimental physics. The human imagination is not easily satisfied. Once we see emptiness as alive, we cannot help but wonder what deeper mysteries it conceals. If the vacuum teems with activity at scales too small to perceive, what happens at scales even smaller, beyond the reach of current theory? At the Planck length, so unimaginably tiny that even protons dwarf it, might the vacuum boil into something stranger still? Could geometry itself fluctuate, space and time bubbling and twisting, the stage of reality reduced to foam? What begins with virtual particles and uncertainty might escalate into a chaos where even light cannot move unperturbed. The vacuum is not still. The closer we look, the more alive it becomes. Quantum mechanics whispers that beneath the apparent calm of empty space, fields never fall completely silent. They thrum with invisible rhythms, a ceaseless activity born of uncertainty. To understand this, imagine a guitar string. Even when no one plucks it, microscopic vibrations ripple across its surface, too faint for the ear to catch. The vacuum is like that, except its vibrations are not in wood and wire, but in the very fields that shape reality. Physicists describe this as quantum fluctuations. These are not particles in the traditional sense, but flickers of possibility. Out of nowhere, pairs of particle and antiparticle appear, borrow a scrap of existence, and vanish almost instantly. They leave no lasting trace, yet their fleeting presence alters the balance of forces in subtle, measurable ways. Virtual photons, for instance, constantly emerge from the vacuum, and their existence explains why charged particles feel forces even across empty space. The emptiness between them is never truly empty, but alive with hidden exchanges. This activity is demanded by the uncertainty principle, a rule so profound it reshapes our idea of reality. It declares that certain properties cannot be known with arbitrary precision. Energy and time are one such pair. If you demand to know the energy of a system with absolute certainty, then its duration becomes unknowable. If you allow a brief moment of uncertainty in time, then energy can fluctuate. It is this loophole that the vacuum exploits. For infinitesimal moments, energy blossoms into existence, creating particles that flash into reality and then disappear. The shorter their lifetime, the greater the fluctuation that can be allowed. Reality itself is licensed to bend its rules, provided the bending happens quickly enough. Though these ghostly particles fade almost instantly, their influence is undeniable. The Casimir effect proves it. When two metal plates are brought very close in vacuum, closer than the width of a human hair, the fluctuating vacuum outside the plates differs from that inside. The imbalance creates pressure, pushing the plates together. This is not science fiction, nor is it a quirk of interpretation. It is a real, measurable force, born of the restless vacuum. In this way, nothingness exerts power over matter, revealing that emptiness is in fact alive with unseen energy. Even more astonishing is the role the vacuum plays on the grandest scales. Cosmologists confront the puzzle of dark energy, the mysterious force driving the acceleration of the universe's expansion. One possibility is that dark energy is nothing more than the cumulative effect of vacuum fluctuations, the sum of all those ghostly particles flickering in and out of existence. If true, then the ultimate destiny of the cosmos is being shaped by the vitality of nothingness. Galaxies will be carried farther apart. Stars will drift beyond each other's horizons. The night sky will dim into silence, all because the vacuum refuses to be truly empty. Yet this revelation brings paradoxes. When physicists attempt to calculate the energy density of the vacuum, quantum field theory predicts an absurdly large number, 120 orders of magnitude greater than what is observed. This discrepancy between theory and observation is the most extreme mismatch in the history of science. It suggests that our understanding of the vacuum is incomplete, that we are missing some deeper principle that cancels or conceals most of its energy. The vacuum, it seems, is alive not only with restless activity, but also with secrets we cannot yet unravel. This is where the mystery deepens. If empty space is alive with energy, if it can bend forces, if it can steer the fate of the cosmos, what does this mean for light? Einstein's principle assures us that light travels at a constant speed through vacuum. But that picture was drawn before the quantum revolution revealed the vacuum's hidden life. Does the seething activity beneath the surface disturb the path of photons? Does light always march at its constant pace? Or is it nudged and scattered in ways too faint to measure with today's instruments? The possibility haunts modern physics. It drives astronomers to study photons from the farthest reaches of the cosmos, where billions of years of travel might amplify even the tiniest disturbances. It inspires theorists to explore new frameworks of quantum gravity, hoping to reconcile the smooth constancy of relativity with the restless vitality of the vacuum. Somewhere between these extremes lies the truth, waiting to be revealed. And so the vacuum, once dismissed as nothing, now stands as a central player in the drama of physics. It is no longer a blank stage, but an actor in its own right, shaping forces, dictating cosmic expansion, and perhaps even whispering to the speed of light itself. Yet questions remain unanswered. What lies at scales smaller still, at the Planck length where geometry itself may fluctuate? Does the vacuum merely ripple with particles, or does it froth like an ocean at storm? The next step in the journey takes us there, into the vision of space-time foam. The picture of vacuum as alive reshapes how we think about reality itself. We are used to separating existence into what is and what is not, into matter and absence. But quantum field theory denies such clean division. The vacuum is not nothing. It is the ground state of everything, a canvas woven of fluctuating fields. It hums beneath every atom, beneath every star, beneath the vastest spaces between galaxies. The restless motion of its unseen fluctuations is as real as the orbits of planets, though hidden from the naked eye. This strange vitality can even touch the most violent phenomena in the universe. Black holes, those prisons of gravity, are expected to be absolute in their silence, swallowing everything, even light. Yet quantum physics says the vacuum near their horizons is restless, birthing pairs of virtual particles. Normally, these pairs annihilate instantly, leaving no trace. But if one falls into the black hole while the other escapes, energy is stolen. The escaping particle becomes real, a whisper of radiation in the dark. This is Hawking radiation, the quantum voice of black holes, a reminder that the vacuum's life force cannot be stilled even by gravity's mightiest prisons. It reveals that nothingness can erode the most absolute something. The vacuum also unsettles our picture of force itself. Every interaction we know, electromagnetism, the strong nuclear force, the weak force, arises from exchanges of particles, many of them virtual. Photons flit invisibly between charged particles. Gluons dart between quarks, mediating their bonds. These are not solid billiard balls, but excitations of the vacuum fields themselves. Without the vacuum's vitality, there would be no forces, no atoms, no chemistry, no life. The void is the womb of structure, the background hum that orchestrates every connection. For all its influence, the vacuum remains elusive. We know it exists because of effects like the Casimir force, because of Hawking radiation in theory, because of the inexplicable acceleration of cosmic expansion. Yet direct exploration is nearly impossible. The fluctuations are tiny, fleeting, hidden beneath the noise of larger phenomena. To capture them directly would require instruments sensitive enough to register changes smaller than anything we can currently measure. This barrier leaves us both certain and uncertain, confident that the vacuum is alive, yet unable to describe its life in full detail. This paradox haunts physics. On one side stands relativity, a theory where vacuum is a perfect stage, smooth and unbroken, through which light travels with unfailing constancy. On the other side stands quantum mechanics, where vacuum is restless, seething, alive with particles forever flickering into and out of being. Both are true, and both are incomplete. To reconcile them is to find the theory of everything, the unified vision of the cosmos. Until then, we live with a contradiction at the heart of science. This contradiction points us toward deeper mysteries. If the vacuum is alive with fluctuations, perhaps geometry itself is unstable at the smallest scales. Perhaps space-time is not smooth, but fractured, bubbling, foaming, a chaos where wormholes spark and vanish like fireflies, where the very concept of distance is uncertain. This was the vision of John Archibald Wheeler in the mid-20th century, when he proposed that space-time at the Planck length may resemble a stormy ocean more than a calm surface. If his vision is correct, then the vacuum is not only alive with particles, but alive with space-time itself, endlessly frothing at the limits of comprehension. The transition is clear. We began with Einstein's cosmic speed limit, the constancy of light in empty space. We then discovered that empty space is never truly empty, but alive with virtual particles and restless fluctuations. Now we must ask whether this activity is only the beginning. If the vacuum is alive at the level of fields, might it also be alive at the level of space-time itself? Might the stage of reality boil and churn, a quantum foam shaping every photon's path? To answer this, we turn to Wheeler's vision and to the frontier where geometry itself may dissolve. In the middle of the 20th century, when the triumph of relativity was already woven into the fabric of physics and quantum theory was reshaping our view of matter, a restless mind looked further. John Archibald Wheeler, a physicist with a gift for vivid imagery, asked what space and time themselves might look like if examined at the smallest imaginable scales. He coined a term that was as poetic as it was unsettling. He called it space-time foam. Wheeler's vision was built on a simple but radical question. If quantum mechanics ensures that no field is ever perfectly still, why should geometry itself be exempt? Space-time is not simply a backdrop, not an inert stage upon which particles perform. It is dynamic, curving in the presence of mass, rippling with gravitational waves. If everything else is subject to quantum uncertainty, perhaps space-time too is restless at the tiniest scales. Perhaps what appears smooth and continuous from afar is, up close, a chaos of fluctuations, bubbling and frothing like the surface of a stormy sea. The scale of this froth is unimaginably small. It is called the Planck length, about 1/10,000,000th of a trillionth of a centimeter. At this length, the ordinary notions of distance and time dissolve. According to Wheeler, space-time itself would not resemble a calm fabric, but a turbulent foam, where wormholes spark into existence and vanish in the blink of an eye, where the geometry of space twists and knots, where even the idea of before and after may lose meaning. Just as water, viewed from far above, looks smooth but up close is filled with bubbles and spray, so space-time from afar seems continuous but may boil with ceaseless activity at its foundation. This was not idle speculation. Wheeler's concept of space-time foam arose naturally from combining the principles of quantum mechanics with general relativity. Quantum mechanics says energy fluctuates at small scales. Relativity says energy curves space-time. Put them together, and the inevitable conclusion is that space-time itself must fluctuate wildly at the Planck scale. The foam is not a metaphor, but the expected face of geometry when viewed under the unforgiving microscope of quantum uncertainty. For most of physics, the foam is irrelevant. Particles, atoms, and even stars are enormously larger than the Planck length, and so space-time appears smooth to them. But Wheeler insisted that at the foundation of reality, the foam was essential. It was there, in that chaos of geometry, that the true nature of gravity, quantum mechanics, and perhaps the entire cosmos would be revealed. To ignore it was to mistake the surface for the depth, the calm appearance for the raging truth beneath. The implications are staggering. If space-time is foamy, then the path of light is not perfectly straight. Photons traveling across billions of light years would not glide effortlessly through an empty void, but stumble and scatter through a frothing sea. Most deviations would cancel, leaving the overall speed of light unchanged to an extraordinary degree. But perhaps, just perhaps, tiny traces of the foam might accumulate over immense distances, altering arrival times, blurring signals, or revealing themselves as subtle noise in the patterns of cosmic light. The foam would not break Einstein's law outright, but it might bend it in whispers too faint to hear without the universe itself as amplifier. Wheeler's vision was both terrifying and beautiful. It told us that reality is not smooth but jagged, not calm but wild, not fixed but alive at every scale. It told us that our greatest theories, relativity and quantum mechanics, though powerful, were incomplete until they could describe the foam together. It told us that emptiness is not the absence of structure, but the most intricate structure of all. The idea of space-time foam changed the way physicists imagine the foundations of the universe. It turned nothing into something, and it demanded that even geometry itself be understood as a fluctuating quantum phenomenon. Yet Wheeler's vision raised as many questions as it answered. Could such foam ever be observed? Could light, traveling across the cosmos, betray its existence? Could experiments on Earth ever probe so tiny a scale? The Planck length is so far beyond our reach that to measure it directly seems impossible. And yet, the very act of imagining the foam transformed the frontier of physics. It became a guiding beacon, a reminder that even the smoothest appearances may conceal the wildest truths. Now, the question sharpens. If space-time foams and churns at the smallest scales, what happens to the constant speed of light? Does light stumble through this chaos, its path jostled by unseen currents? Does its constancy survive even here, or does it reveal hairline fractures when tested against the turbulence of the vacuum? These are the questions that carry us from Wheeler's vision to the next stage of the story, where we consider light itself moving through a frothing universe. Wheeler's vision of space-time foam was not meant to be comfortable. It challenged the idea that geometry was smooth, continuous, and eternal. Instead, he pictured a realm at the Planck scale, where space boiled like a cauldron, where wormholes opened and closed in an instant, where time itself fractured into fragments. To grasp what this means, imagine shrinking yourself down until atoms are colossal, until protons stretch across horizons. At that level, the familiar order of reality vanishes. The coordinates we use to measure length and duration lose meaning. Up close, space-time may be more like a storm-tossed ocean than a calm sheet. Physicists sometimes compare this foam to a frothing glass of water. From a distance, the surface looks flat. Bring your eye closer, and you see waves and bubbles. Zoom closer still, and the surface becomes chaotic, impossible to pin down. In Wheeler's analogy, the Planck length is the scale where this chaos begins. It is unimaginably tiny, 10 to the power of -35 meters, far smaller than any particle we know. At that depth, quantum fluctuations in energy are so extreme that they twist the geometry of space itself, producing bubbles and tunnels, warping the very notion of a straight line. If this vision is true, then even the act of measurement loses clarity. How can you measure a distance if the ruler itself is fluctuating? How can you speak of time intervals if the flow of time is itself unsteady? Wheeler believed that the foam would erase certainty at the deepest level, reducing geometry to probabilities, distances to shifting clouds of possibility. Just as quantum mechanics blurred the picture of particles into waves of probability, space-time foam would blur the picture of geometry into a storm of possibilities. This raised profound questions. What would a photon experience as it moved through such a landscape? To us, light seems to travel in straight lines, obeying the constant pace Einstein described. But in a foamy space-time, the path may jitter, deviate, scatter. The effects may be too small to detect in ordinary circumstances. Yet over billions of light years, even the tiniest disturbances might accumulate into something observable. Wheeler did not claim to know the details. He only insisted that at the Planck scale, the very concept of smooth geometry breaks down. His idea resonated because it seemed inevitable. Combine relativity, which tells us energy curves space-time, with quantum mechanics, which tells us energy fluctuates constantly, and the result is unavoidable. Space-time cannot remain smooth under such conditions. It must ripple, foam, and churn. Wheeler gave this picture a name that was both scientific and poetic: space-time foam, a phrase that carried his vision into the imagination of generations of physicists. The foam became a guiding metaphor in the search for quantum gravity. It reminded researchers that the smooth geometry of Einstein's equations might be only an approximation, like the smooth surface of water that conceals its molecular chaos. The true theory of everything would have to account for this deeper turbulence to show how foam at the Planck scale gives rise to the smooth spacetime we experience at larger scales. The challenge was daunting, but Wheeler's imagery gave it a shape, something to chase. And so the question sharpened. If spacetime is foamy, then light cannot pass through it unchanged. The constancy of its speed may be tested against this churning background. Could deviations be detected? Could cosmic messengers reveal what earthly instruments cannot? The stage was set for new ways of probing the universe, ways that might reveal whether Wheeler's vision was a poetic dream or a hidden truth of reality. At the heart of Wheeler's vision lies both a promise and a problem. The promise is that spacetime foam may be the long-sought key to uniting relativity and quantum mechanics, the two towering but incomplete frameworks of modern physics. The problem is that the foam resides at scales so small that no human instrument can hope to probe it directly. The Planck length, that mysterious 10 to the power of minus 35 meters, is a realm forever beyond microscopes, particle accelerators, or even the most ambitious of engineering projects. It is smaller than the width of a proton by a factor so immense that the mind struggles to hold it. To touch the foam is to touch the ultimate foundation of reality, and yet we are locked outside by the sheer magnitude of the scale difference. Still, the human mind is not so easily deterred. Physicists have sought clever ways to search for evidence of the foam indirectly. If light must travel through this frothing geometry, then perhaps traces of its passage remain in the signals we observe. Wheeler himself imagined photons skittering through bubbles of space-time, their paths slightly jostled, their timing minutely altered. One photon might be delayed by an imperceptible fraction, another nudged by a fleeting wormhole. Across short distances, the effect would be negligible, drowned in noise. But over billions of years and billions of light years, the tiny tremors might accumulate into something detectable. Here, the cosmos becomes our laboratory. Gamma-ray bursts, quasars, pulsars, and distant galaxies all send streams of photons across the abyss of space. Each photon is like a test particle, a probe launched through the vacuum. If spacetime foams, then the distribution of arrival times, the coherence of the signals, the sharpness of the patterns may betray it. Some researchers have searched for blurring in images of distant galaxies, for random scatter that cannot be explained by ordinary physics. Others have hunted for slight delays between high-energy and low-energy photons from the same cosmic event. These experiments are attempts to peer into the foam by amplifying its faint effects across cosmic distances. So far, the results are stubborn. Light behaves with eerie constancy. The photons arrive together, their coherence intact, their timing precise. No blurring beyond the expected appears in distant images. No delays beyond known causes emerge in gamma-ray bursts. The foam, if it exists, hides its presence well. This leaves physicists torn between confidence in Einstein's postulate and curiosity about Wheeler's vision. Perhaps the foam is real, but subtler than imagined. Perhaps new instruments, with greater sensitivity, will one day detect it. Or perhaps spacetime at the Planck scale is not foamy at all, but something stranger, something beyond even Wheeler's vivid metaphors. What is certain is that Wheeler changed the way we think about emptiness. His spacetime foam transformed the vacuum from a passive background into a restless frontier. It framed the search for quantum gravity not as an abstract exercise, but as a quest to understand the texture of reality itself. Foam may or may not be the final answer, but the idea opened a door that cannot be closed. We now know that the smooth spacetime of relativity is incomplete, that something richer, more chaotic, or more elegant must lie beneath. And so, the chapter turns. We began with Einstein's constant. We descended into the restless life of the vacuum. And now, we have seen Wheeler's vision of foam. The next step is to ask what happens when light itself is forced to cross such a storm. Does it stumble? Does it scatter? Does it reveal the chaos beneath? To explore this is to enter the heart of the mystery, to consider light in a frothing universe. Imagine a single photon, the smallest packet of light, setting out on a journey from a distant galaxy. Its birthplace may be the violent core of a star collapsing into a black hole, or the blazing jets of matter spiraling from a supermassive engine at the center of a quasar. With no mass, no charge, and no rest, it slips into the vacuum and begins its voyage across billions of light years. If Einstein's vision is absolute, then this photon will travel unwaveringly at its constant pace, never faltering, never straying, until it meets the waiting lens of a telescope on Earth. But what if Wheeler's vision of space-time foam is true? What if the vacuum is not smooth but frothing? Then the path of this photon may be less certain, like a sailor steering across an ocean, not of calm water, but of ceaseless waves. At human scales, the foam is invisible. A beam of light traveling across a laboratory, across a city, even across the solar system appears to move in flawless straight lines. Relativity holds without exception. But at the Planck length, the photon may encounter disturbances in the geometry of space-time itself. Tiny wormholes might open and close, fluctuations in curvature may twist its trajectory, microscopic bubbles may scatter its wave. Each effect would be infinitesimal, vanishing in the noise of ordinary observation. Yet the photon's journey is long, unimaginably long. Like a traveler who feels no discomfort from a single ripple, but may be wearied by crossing an ocean of them. The photon may accumulate subtle delays or distortions as it traverses billions of light years. This possibility fascinates physicists because it offers a way to test the foam without touching the Planck scale directly. If even the faintest traces of the foam alter photons, then cosmic light itself becomes a messenger, carrying information about the nature of space-time. Photons from gamma-ray bursts, for instance, are ideal test subjects. They are born in violent explosions billions of light years away, and they arrive in a sudden, sharp pulse. If space-time foam jostles them, then higher energy photons may be delayed compared to lower energy ones, their arrival times slightly out of sync. Over such immense distances, even minuscule fluctuations may reveal themselves. To grasp how this works, imagine a marathon with billions of runners starting together. If every runner takes the same route across a smooth track, they should arrive nearly together, separated only by differences in strength or speed. But if the track is full of potholes and barriers, even tiny ones, then some runners will be slowed, others detoured. At the finish line, the once unified crowd will be dispersed. Light traveling through foam would show a similar effect. Photons of different energies might no longer arrive in perfect unison, betraying the turbulence of the vacuum. So far, experiments have searched for these delays with relentless precision. Satellites like the Fermi Gamma Ray Space Telescope have monitored gamma-ray bursts across the sky, recording the arrival times of photons spanning a wide range of energies. The expectation is clear. If foam jostles light, high-energy photons may stumble more than low-energy ones, arriving seconds or minutes later after traveling billions of years. Even the smallest lag could be a signal, a whisper from the Planck scale itself. And yet, the whispers remain faint. Photons arrive with astonishing synchrony. Bursts billions of light years away show no measurable smearing, no delays beyond what can be explained by the astrophysical processes that created them. The foam, if it exists, leaves no obvious fingerprints. This result both strengthens Einstein's principle and deepens the mystery. Light, it seems, remains constant even when tested across the grandest distances, across the very fabric of the universe. Still, the search is not over. The absence of evidence does not prove the absence of foam. It may simply mean that the foam is subtler than we expect, or that its effects average out, leaving light largely untouched. Perhaps space-time churns with bubbles too small or too fleeting to alter a photon's journey in measurable ways. Or perhaps the foam manifests in forms we have not yet imagined, producing effects not of delay, but of polarization, coherence, or subtle noise hidden in the spectrum of light. The possibility remains irresistible. To study light in a frothing universe is to peer into the edge of physics itself. It is to ask whether the constancy of light speed is absolute or approximate, whether relativity reigns unchallenged or conceals deeper structures. It is to use the cosmos itself as a laboratory, with every distant photon a test particle, every burst of light a probe of the Planck scale. The search is as much philosophical as scientific, for it challenges our notions of smoothness, certainty, and law. What if the constancy of light is not the ultimate truth, but a grand approximation that holds only because space-time foam is too small to matter at ordinary scales? What if the true face of reality is turbulent, restless, alive, and light is only skimming across its surface, appearing smooth while the depths churn unseen? These questions press us forward, from speculation to observation, from Wheeler's metaphor to the harsh test of data. The next step is to turn our eyes to the universe's most violent beacons, gamma-ray bursts, and see what secrets their photons carry across the cosmic sea. Light in a frothing universe is not only a scientific hypothesis, but a cinematic vision. Imagine again that lone photon leaving its birthplace, fired outward by a cataclysmic event so far away that entire species may rise and fall before its journey is done. It moves through the great ocean of space-time, carrying with it the record of its origin. To us, this photon seems unwavering, a perfect messenger obeying the constant speed limit Einstein revealed. But in Wheeler's universe of foam, the photon is like a boat tossed upon waves too small to be seen, too quick to be charted, but always there. What would this mean for our understanding of constancy itself? Physics has long thrived on the assumption that laws are universal, unchanging, absolute. The speed of light is not just another constant, it is the bedrock upon which causality, relativity, and modern technology rest. If foam can disturb photons, even slightly, then the constancy of light is not an unbreakable commandment, but an emergent feature, a stability that arises only on average across scales larger than the Planck length. This would be a profound shift in perspective. The ultimate law would not be the constancy of light, but the restless turbulence of space-time itself, from which constancy emerges like calm from chaos. Such ideas test the boundary between science and philosophy. If light is delayed by foam, how do we define simultaneity across the cosmos? If paths of photons are jostled, what does it mean for space-time to be measurable? Einstein's relativity was built upon thought experiments with light signals, using them to synchronize clocks and define distances. If light itself is no longer perfectly reliable, then the very foundations of relativity would tremble. Perhaps they would be replaced not by collapse, but by a deeper framework in which foam and fluctuations are the true reality, and smooth constancy the illusion. The implications extend to cosmology. Our understanding of the universe's expansion, of the age of galaxies, of the timing of cosmic events, all rely on the assumption that light travels at one unchanging pace. If space-time foam slows photons even slightly, then every measurement across cosmic distances would need correction. Galaxies might be farther or closer than we believe. The timeline of cosmic history might be subtly distorted. In such a scenario, our entire picture of the universe's evolution would need to be redrawn with foam in mind. Yet this speculation must be balanced against experiment. Every observation so far has confirmed light's constancy with exquisite precision. Pulsars flash with metronomic regularity, their signals racing through space without detectable scatter. Gamma-ray bursts arrive in sharp spikes, photons of different energies keeping step across billions of light years. Quasars shine without the random blur one might expect if foam jostled their light. These are powerful testimonies to Einstein's postulate, and they constrain the possible forms that space-time foam could take. If the foam exists, it must either be too subtle to disturb photons, or structured in a way that preserves their constancy on average. Still, absence of evidence is not evidence of absence. The cosmos continues to offer new opportunities to test light against foam. more sensitive telescopes, higher resolution detectors, and longer baselines of observation expand the search. Each photon is a messenger, each burst of cosmic light a new experiment. The dream is that one day, amid the billions of signals, we may catch a deviation, a trace, a faint scar that reveals the foam. Such a discovery would not only confirm Wheeler's vision, but also open the door to a new physics, a union of relativity and quantum theory long sought but never achieved. For now, we live in the tension between theory and observation. Wheeler's vision tells us that foam is inevitable. The marriage of relativity and quantum mechanics demands it. Einstein's postulate tells us that constancy is unbroken, photons remain faithful to their pace. The cosmos itself seems to conspire to keep the secret, offering light as both messenger and mystery. Perhaps this tension is temporary, the prelude to a discovery that will shatter our assumptions. Or perhaps it is permanent, the signature of a universe whose deepest truths are forever hidden from our reach. From the viewpoint of human imagination, the story is irresistible. Light gliding through a stormy sea of space-time, photons stumbling across bubbles and wormholes, constancy emerging from chaos. These images blend science with myth. They remind us that our most trusted constants may themselves be part of a larger, wilder reality. The next step is to press the test further, to use the most violent events in the cosmos as natural laboratories. For in gamma-ray bursts, the universe gives us flashes of light so sharp, so distant, and so powerful that they may finally reveal whether the foam is real. The idea of light struggling through a frothing universe is as unsettling as it is mesmerizing. In our ordinary experience, photons seem flawless. They streak across the laboratory, across the sky, and across interplanetary space without hesitation or flaw. The constancy of their speed feels absolute, something we can trust more than any other principle in nature. Yet, when we imagine them traveling across billions of light years, the thought of space-time foam gnaws at our certainty. Perhaps the vacuum is not a placid emptiness, but a stormy sea. And perhaps every photon is forever negotiating with turbulence too small for us to see. If this is true, then the photons we detect are survivors. Each one that reaches our telescopes has endured a journey through countless fluctuations. Some may have been delayed by fractions of a second, others nudged off course, others shifted in phase or polarization. The deviations would be invisible across short distances, drowned in the noise of ordinary measurement. But across cosmic baselines, they may build into signals that reveal the froth beneath. A single photon may tell us nothing, but billions of them, arriving from a single cataclysm, may carry the signature of foam imprinted in their distribution. This is why astronomers speak of light as both messenger and test. Photons are not merely images, not merely records of distant events. They are probes, each carrying in their timing, their coherence, and their alignment a story about the geometry of the vacuum. If space-time foams, then photons should feel it, even if only faintly. In this way, light becomes the most subtle detector imaginable, one spread across the entire universe, one capable of probing scales far beyond any particle accelerator or laboratory on Earth. The challenge, of course, is separating the whisper of foam from the roar of astrophysical processes. A gamma-ray burst, for instance, is a chaotic eruption. Photons of different energies are not emitted all at once, but in complex cascades that unfold over seconds. If high-energy photons arrive later than low-energy ones, is this the signature of foam, or simply a feature of the explosion itself? To claim discovery, physicists must disentangle the intrinsic behavior of the source from the possible influence of the journey. It is like listening for a faint echo while standing in the middle of a thunderstorm. Despite these difficulties, the search presses forward because the stakes could not be higher. If evidence of foam is ever found, it would be the first glimpse of physics at the Planck scale. It would be the long-awaited bridge between relativity and quantum theory, the beginning of a new era in our understanding of reality. It would tell us that space-time is not smooth, that Einstein's postulate is not absolute, and that constancy itself is born from chaos. Such a discovery would reshape not only physics, but philosophy, forcing us to rethink what it means for a law of nature to be fundamental. And yet, the opposite outcome is equally profound. If light remains perfectly constant, even across billions of light years, if photons never stumble, never falter, then this too is a revelation. It would tell us that relativity holds deeper than we imagined, that the foam either does not exist or is structured in such a way that its effects cancel perfectly. It would suggest that space-time may not be turbulent but ordered, that smoothness may be fundamental after all. This would narrow the search for quantum gravity, ruling out many speculative ideas and guiding us toward those that preserve constancy as a sacred principle. In this way, the question of light in a frothing universe becomes more than a technical problem. It becomes a crucible for theory itself. Do we live in a cosmos where laws are emergent, born of turbulence, where constancy is an illusion carved from chaos? Or do we live in a cosmos where smoothness is real, where the vacuum is not a storm but a perfect stage, where Einstein's vision reigns without compromise? Each photon that reaches us brings us closer to an answer, even if the answer is hidden in silence. And so, the search continues. Telescopes watch the skies for gamma-ray bursts, pulsars, quasars, and flares, each a natural experiment conducted on scales we could never hope to engineer. Each observation sharpens the limits, tightening the noose around Wheeler's foam. Perhaps one day, the signals will reveal themselves. Perhaps one day, the froth of space-time will be caught in the net of photons. Until then, light remains both faithful and mysterious, a constant that may conceal a secret, a messenger that may one day betray the froth it has traveled through. The chapter closes on this tension, a tension between certainty and speculation, between Einstein's constancy and Wheeler's foam. Light in a frothing universe is a possibility that haunts physics, not yet proven, not yet disproven, a question suspended at the edge of experiment. And so we turn to the next act, to the violent flashes of gamma-ray bursts, where the test of constancy and foam becomes sharpest, and where the universe itself seems to dare us to find the truth. When the universe wishes to test our deepest theories, it does not ask our permission. It erupts. Gamma-ray bursts are among the most violent events ever observed, explosions so bright that for a few seconds, they outshine entire galaxies. They occur when massive stars collapse into black holes, or when neutron stars collide in cataclysmic mergers. In those brief moments, they release torrents of photons, many of them with energies millions of times higher than the light we see with our eyes. And because these bursts often occur billions of light years away, their photons travel across nearly the entire observable universe before arriving at Earth. In their fury and distance, gamma-ray bursts become natural experiments, laboratories built by the cosmos itself. For physicists seeking traces of space-time foam, gamma-ray bursts are a gift. They provide sudden flashes of photons born together in the same event, photons spanning a wide range of energies, all racing toward us at light speed. If Wheeler's vision of foam is correct, then higher energy photons may be jostled more than their lower energy siblings. Over billions of years, even the tiniest difference would accumulate into measurable delays. By comparing arrival times, physicists hope to detect whether the foam is real, whether the constancy of light is as absolute as Einstein claimed, or whether it hides subtle cracks revealed only across cosmic distances. The principle is simple but profound. Imagine again the marathon of photons, billions of runners leaving the starting line together. If the track of space-time is perfectly smooth, then they all arrive together, regardless of energy. If the track is foamy, riddled with microscopic potholes and turbulence, then higher energy runners stumble more, arriving moments behind. The difference may be milliseconds, seconds, or minutes, depending on the scale of the foam and the distance of the burst. To measure such delays is to probe space-time itself, to ask whether the vacuum is smooth or turbulent. The first serious attempts to use gamma-ray bursts as experiments came in the late 20th century, when detectors on satellites began capturing these extraordinary events. Instruments like the Compton Gamma Ray Observatory revealed that bursts were not rare curiosities, but frequent flashes scattered across the sky. Their distribution was uniform, suggesting they occurred far beyond our galaxy at cosmological distances. This was the first hint of their true power. If the bursts were billions of light-years away, then their photons were ideal messengers for testing fundamental physics. Each one had crossed an ocean of space-time, and any foam along the way might have left its mark. The challenge was precision. To detect differences in arrival times, instruments must record photons with exquisite timing accuracy. The Fermi Gamma Ray Space Telescope, launched in 2008, was designed for this purpose. Its detectors can measure the arrival of individual photons across a broad spectrum of energies, down to fractions of a millisecond. By capturing bursts from billions of light-years away, Fermi turns each event into a test of Einstein's constancy and Wheeler's foam. Results have been striking. In many cases, photons of vastly different energies arrive together, separated only by the astrophysical complexity of the explosion itself. Some of the highest energy photons ever recorded, carrying tens of billions of electron volts, have arrived within milliseconds of their lower energy counterparts, even after journeys of billions of years. This remarkable synchrony places severe limits on any theory of spacetime foam. If the foam exists, its influence must be far weaker than many models predicted. But the search is not over. Gamma-ray bursts are diverse, each with its own signature, its own timing, its own chaotic unfolding. Some bursts show hints of delay, though disentangling the intrinsic behavior of the source from the possible effects of foam is difficult. Was a photon delayed because space-time jostled it, or because it was emitted slightly later in the explosion? This uncertainty keeps the question alive, fueling debate and pushing the demand for more data. Each burst is another chance, another test, another whisper from the depths of the universe. And so gamma-ray bursts serve as both spectacle and experiment. They remind us that the cosmos is violent, unpredictable, and vast beyond measure. Yet they also give us tools to probe its most subtle secrets. Through them, we may learn whether Einstein's cosmic speed limit is truly absolute, or whether light itself is humbled by the foam of space-time. Gamma-ray bursts test more than technology. They test our patience, our theories, and even our imagination. Each one begins suddenly, without warning, often lasting only a few seconds. The universe does not schedule them for our convenience. Astronomers must be ready at any moment, instruments tuned and waiting to capture their fleeting light. When a burst occurs, detectors on board satellites register a flood of photons, and ground-based telescopes swivel within seconds to catch the fading afterglow. Every captured photon is a clue, a piece of evidence in the cosmic experiment being run without our control. The allure of these bursts lies in their scale. Consider one such event detected in 2009, known as GRB 090510. It came from more than 7 billion light-years away, an explosion that occurred when the universe was barely half its present age. Among the countless photons it hurled across the cosmos was one carrying over 30 billion electron volts of energy, a single particle of light far more energetic than anything our particle accelerators on Earth can create. And yet, this photon arrived at nearly the same moment as its lower energy companions. It had crossed 2/3 of the observable universe and still refused to show any evidence of stumbling. This synchronicity was not expected if Wheeler's foam acted strongly upon light. Models that predicted large deviations were ruled out in a single stroke. The constancy of light had survived another challenge, its authority reinforced by the universe itself. But physicists were not ready to abandon the search. The foam could still exist, subtler than imagined, exerting effects too faint to be captured, even in such extraordinary events. Perhaps its influence cancels out on average, or perhaps its fingerprints appear only in rare conditions not yet observed. The difficulty lies in disentangling signal from source. A gamma-ray burst is not a simple beacon, but a storm. It unfolds in multiple stages, from the violent birth of jets within collapsing stars or merging neutron stars, to the afterglows that linger for days across the electromagnetic spectrum. Photons of different energies may be emitted at different times, not because of foam, but because of the astrophysics of the explosion. This means that even when high-energy photons arrive later than their low-energy counterparts, caution is required. Is this delay evidence of space-time turbulence, or simply a reflection of the burst's chaotic inner workings? The line between astrophysics and fundamental physics is fine, and crossing it without care risks mistaking noise for discovery. Still, the potential is irresistible. Gamma-ray bursts offer conditions no human machine can replicate. They send photons across billions of light years, a baseline longer than any experiment we could build. They generate energies orders of magnitude greater than any collider can reach. They provide timing sharp enough to test constancy at scales unimaginable a century ago. The universe is not merely a backdrop, but an active partner in our experiments, hurling tests at us in the form of cataclysms. What makes the search so cinematic is the duality of these bursts. They are both destroyers and teachers. Each one represents a star's death or a collision so violent it reshapes entire systems. Yet out of this violence comes information, pure and precise, photons carrying whispers of the vacuum. The cosmos burns itself to give us clues about its deepest laws. In those moments, death and knowledge become one. The hunt for foam in gamma-ray bursts has so far yielded silence, but silence is data. Each null result narrows the range of possibilities, pushing theorists to refine models and experimenters to sharpen tools. It tells us that if foam exists, it must be quieter, subtler, more elusive than once dreamed. But silence is not defeat. It is the patient voice of the cosmos, reminding us that truth does not reveal itself easily. And so astronomers keep watching, detectors keep listening, and every burst becomes another chance to catch space-time in the act of foaming. Somewhere among the billions of photons, there may be one that betrays the secret. Somewhere in the silence, there may be a whisper too faint for our current ears but waiting for the next generation to hear. The universe is patient. It has been foaming, or not, for over 13 billion years. Our search has only just begun. Gamma-ray bursts remain some of the most enigmatic and powerful events in the universe. They erupt without warning, outshining entire galaxies for a few brief seconds, and then fade back into silence. For physicists, they are more than cosmic fireworks. They are precision experiments written across billions of light years. Each burst offers a chance to probe whether space-time itself is smooth or foamy, whether Einstein's constant is inviolable, or only an approximation that hides turbulence beneath. The methodology is straightforward in principle. Photons of many energies are born together in the same violent explosion. They should arrive together if the fabric of space-time is as smooth as relativity describes. If instead the universe froths at the Planck scale, the higher energy photons might be slowed ever so slightly, their journey hindered by bubbles and twists invisible to ordinary detection. The longer the journey, the greater the chance that such tiny delays will accumulate into something measurable. Bursts occurring billions of light years away thus become natural timekeepers, their arrival patterns potential signatures of foam. What astronomers have found so far is both reassuring and provocative. In many cases, photons spanning vast ranges of energy have arrived in lockstep, as if space-time were perfectly smooth. In others, small irregularities appear, but disentangling them from the astrophysical chaos of the source is difficult. A collapsing star is not a metronome. It does not emit photons in perfect synchrony. Some delays may arise simply from the complexity of the explosion itself. To claim evidence of foam, physicists must first strip away every other possible cause. This challenge is daunting, but it has not deterred the search. The beauty of gamma-ray bursts as experiments is that the universe conducts them for us. No machine on Earth can replicate their conditions. Our greatest particle accelerators fall short by orders of magnitude in both energy and distance. But a gamma-ray burst sends photons across the cosmos, testing light's constancy over scales that human technology cannot dream of. Our role is to build detectors sensitive enough to capture the signals and clever enough to interpret them. In this sense, every burst is a collaboration between humanity and the universe itself. As the decades pass, the silence of these tests becomes its own kind of answer. If space-time foam exists, it is quieter than Wheeler's first visions suggested. It may be structured in ways that cancel its influence, or it may leave marks that we have not yet learned how to recognize. Perhaps its effects lie not in timing, but in polarization, not in arrival delays, but in subtle statistical noise across billions of photons. The absence of obvious evidence is not the end of the story. It is an invitation to look deeper, to broaden the scope of what counts as a signature. For now, gamma-ray bursts serve as a reminder of both the power and humility of science. They show us the grandeur of the cosmos, its capacity to unleash unimaginable energies. They also show us the patience required to unravel its secrets, the care needed to avoid mistaking chaos for law. Each burst is both a spectacle and a question. Does light stumble through space-time foam, or does it move unperturbed across the frothing depths of reality? The answer remains elusive, but the search itself brings us closer to understanding. And so this chapter closes with the sense of a stage being set. Gamma-ray bursts have given us powerful tools, sharpened our theories, and refined our expectations. They have not yet given us proof of foam, but they have shown us where to look and how to listen. The next step is to widen the search beyond bursts, to quasars, pulsars, and galaxies, to see if the cosmos elsewhere can confirm what bursts alone cannot. The hunt continues, and with it, the promise that one day the silence will break. The search for space-time foam does not end with gamma-ray bursts. Those fleeting flashes offer extraordinary laboratories, but they are not the only messengers that cross the cosmic sea. Astronomers and physicists have turned their attention to other beacons of the universe, using every form of light they can capture to probe whether reality is smooth or foamy at its foundations. Each signal, whether from a pulsar, a quasar, or a distant galaxy, becomes part of the hunt, another attempt to catch the whispers of Wheeler's vision in the act. Quasars, the blazing hearts of galaxies powered by supermassive black holes, shine with staggering brightness across billions of light years. Their light, steady and intense, provides long baselines for testing the clarity of the vacuum. If space-time foams, the light from quasars should not arrive as sharp and coherent as it does. It should blur, scatter, lose focus, as if passing through frosted glass. Yet telescopes reveal quasars in crisp detail, their light refusing to betray any turbulence along the way. The images set strict limits on how violently space-time can froth. If foam exists, it must operate at scales even smaller or subtler than Wheeler first imagined. Pulsars, too, serve as cosmic probes. These neutron stars spin with such precision that their beams of light sweep past Earth like the ticks of a cosmic clock. Some rotate hundreds of times per second, their pulses arriving with remarkable regularity. If foam jostled photons, the pulses should smear or jitter after traveling across interstellar space. Instead, pulsars keep time with astounding accuracy, their signals consistent across years and decades. This reliability again tightens the limits, suggesting that if the vacuum foams, its influence on photons must be faint beyond our current detection. Other experiments look to the light of entire galaxies, their collective emissions serving as beacons from the early universe. If space-time foam distorted light, distant galaxies would appear fuzzier than nearby ones, their features blurred by countless tiny fluctuations. Yet modern telescopes, including the Hubble Space Telescope, have captured distant galaxies in striking clarity. Their light has crossed billions of years without evidence of scattering from foam. Each sharp image narrows the possibilities, pushing the idea of observable foam further toward the horizon. The consistency of these results has begun to frustrate as much as it inspires. Einstein's postulate of constancy continues to withstand every cosmic test, while Wheeler's vision of foam remains hidden. The foam may be real, demanded by the marriage of relativity and quantum mechanics, but its effects may be forever beyond our reach. Or perhaps our understanding of the foam is incomplete, and it manifests in ways we have not thought to measure. The silence of the data is both a comfort and a mystery, yet the hunt does not relent. New instruments sharpen the search. Interferometers push the limits of timing precision. Telescopes extend their reach deeper into the universe, and detectors sensitive to polarization probe, where the foam leaves its mark in subtler ways. Theories evolve alongside the observations, some suggesting that foam respects light's constancy perfectly, others proposing violations so small they require unimaginable sensitivity to detect. The interplay between speculation and data continues, each guiding the other forward. The quest for foam is not only about physics, it is about the human spirit of inquiry. We are driven to ask whether the universe is truly smooth, whether constancy is fundamental or emergent, whether the deepest layers of reality are calm or chaotic. Even when the data refuse to confirm our suspicions, the very act of searching reshapes our imagination. Each null result teaches us as much as a discovery would, reminding us that science is not only about answers, but also about the boundaries of what can be known. The story of light's constancy has grown richer with every experiment. Gamma-ray bursts, quasars, pulsars, galaxies, each has spoken, and each has said the same thing, that photons do not stumble, that space-time may be smoother than Wheeler's foam suggests. But the silence cannot quiet the question. Perhaps we are only at the threshold of sensitivity, and the foam lies just beyond. Or perhaps its reality demands a new kind of observation, one that we have not yet imagined. Whatever the truth, the hunt continues, fueled by curiosity, as vast as the cosmos itself. The search for space-time foam stretches further, beyond gamma-ray bursts, into every corner of the cosmos where precise light can be found. Quasars, pulsars, and galaxies serve as beacons, each offering new ways to test whether light stumbles through a frothing universe. Quasars are especially valuable. These cosmic lighthouses blaze across billions of light years, powered by supermassive black holes devouring matter at their centers. Their light is intense and sustained, traveling vast distances before it reaches Earth. If space-time were foamy, photons would scatter, their images blurred, as though viewed through frosted glass. But telescopes capture quasars in remarkable clarity, their sharpness surviving unimaginable journeys. This sharpness sets limits on how chaotic space-time can be. The foam, if present, must be delicate, leaving little or no mark on their light. Pulsars add another layer of precision. These rotating neutron stars flash beams of radiation that sweep across Earth like cosmic clocks. Some pulsars tick hundreds of times per second, their timing so exact that even millisecond variations can be noticed. If photons stumbled through foam, these signals should smear or jitter. Instead, pulsars keep time with astounding stability, suggesting again that foam's influence, if real, lies beneath our ability to detect. The vacuum seems smoother than Wheeler's stormy vision would suggest. Distant galaxies too play their part. Their collective starlight travels across billions of years, and still astronomers see their structures clearly. Hubble and other telescopes reveal spiral arms, star-forming regions, and glowing cores, even in galaxies that formed soon after the Big Bang. If foam blurred their light, those features would fade into haze. But clarity persists, adding weight to the idea that light's constancy survives across the deepest cosmic distances. For many scientists, these results inspire both awe and frustration. Awe, because Einstein's law of constancy stands unbroken even against such extreme tests. Frustration, because Wheeler's foam remains hidden, neither proved nor disproved. its existence still demanded by theory, but elusive in practice. The hunt for signs continues, fueled by both curiosity and persistence. Perhaps foam exists, but affects light in ways more subtle than delay or blur. Perhaps it changes polarization, or leaves faint statistical imprints across vast datasets. Or perhaps our models of foam must evolve, pointing us toward new ways of looking altogether. What unites all these efforts is the spirit of inquiry. Even without a positive detection, each observation pushes us closer to understanding what space-time truly is. Every quasar imaged in clarity, every pulsar tick preserved in precision, every galaxy seen sharp at the edge of time, tells us something about the fabric of the universe. If foam exists, it is not the wild turbulence of Wheeler's earliest metaphor, but something quieter, more elusive, more deeply woven into the laws of physics. And yet, the silence itself is instructive. By refusing to show us obvious evidence, the cosmos forces us to refine our questions, sharpen our instruments, and deepen our imagination. The absence of foam in our current measurements does not end the search. It sets the stage for even more ambitious experiments, ones that may finally push beyond the limits of today's vision. The hunt for space-time foam has become one of the most delicate pursuits in physics. It is not a chase for roaring signals or obvious discoveries, but for whispers hidden in the noise of the universe. Every experiment so far, whether with gamma-ray bursts, quasars, pulsars, or distant galaxies, has spoken in the same voice. Light is constant. Photons do not stumble. Space-time, if it foams, keeps its turbulence buried so deeply that it leaves no clear mark. Yet scientists do not give up, for the stakes are too high. The existence of foam would reveal the first direct evidence of quantum gravity, the long-sought union of relativity and quantum mechanics. It would show that space-time itself is subject to uncertainty, that geometry is not smooth but restless. It would transform physics, opening doors to new theories and perhaps new technologies. To abandon the search would be to abandon one of the most profound questions we can ask. The tools of the hunt continue to evolve. Modern telescopes push to higher precision. New detectors measure polarization with exquisite accuracy, and instruments yet to be built promise to expand the search further. Quantum sensors, gravitational wave observatories, and next-generation space telescopes may all contribute to the quest. Each technology adds a new dimension, a new way to ask whether space-time is smooth or foamy. Even if photons remain constant, other particles or forces might carry signatures of turbulence, offering alternate windows into the Planck scale. The theories evolve as well. Some suggest that foam may not disturb photons directly, but instead alter the propagation of gravity itself. Others propose that foam manifests only statistically, its effects too subtle to be seen in single photons, but visible across enormous datasets. Still others argue that foam respects Lorentz invariance perfectly, hiding its influence until we discover entirely new ways to measure. In every case, the silence of the data does not end the story. It sharpens it, forcing theorists to refine their ideas, to search for signatures more subtle, more elusive, but still real. And so the search becomes philosophical as much as physical. What does it mean if foam remains forever beyond detection? Is it real but hidden, like the atoms once suspected but unseen? Or is it only a metaphor, a useful picture that must eventually give way to a more precise framework? Science lives in this tension, in the space between certainty and speculation. The hunt for foam may never yield the dramatic confirmation Wheeler imagined, but it will continue to shape our understanding of reality, guiding us toward the edges of what is possible to know. For now, the verdict remains the same. Light is constant. Space-time, at least in the ways we can measure, is smooth. But the absence of evidence is not the end. It is the beginning of a deeper question. How can the universe appear so calm when every theory tells us it should boil? What principle hides the foam? or cancels its influence, or keeps it forever out of reach? To answer this, we must turn to theories that aim to unite relativity and quantum mechanics, frameworks that promise to explain not only whether foam exists, but why light behaves as it does. The silence of experiments leaves the mystery unresolved. Light seems constant across every distance we can measure, yet quantum mechanics and relativity still cry out for reconciliation. Wheeler's foam remains unseen, but the tension between smooth spacetime and restless quantum fields demands explanation. To move forward, physicists turn to theories of quantum gravity, frameworks that attempt to unite Einstein's vision of curved geometry with the probabilistic world of particles. These theories are bold, mathematical, and often speculative, but they offer glimpses of what may lie beneath the calm surface of the cosmos. One of the most ambitious is string theory. In this framework, the particles we observe are not points, but tiny vibrating strings, their modes of vibration giving rise to mass, charge, and force. Strings require extra dimensions beyond the familiar 3 of space and 1 of time, hidden dimensions curled up so tightly they escape detection. In this picture, space-time itself is not fundamental, but emergent, woven from the dynamics of strings. The constancy of light, then, may not be an absolute law, but a property arising from the structure of string vibrations. Some variations of the theory predict that Lorentz invariance, the principle at the heart of relativity, may be subtly violated at extreme energies. If so, then photons of different energies could travel at slightly different speeds, an echo of foam written into the mathematics of strings. Another contender is loop quantum gravity. Rather than treating spacetime as continuous, it describes it as a network of discrete loops, woven into a fabric that resembles a vast cosmic spin lattice. At ordinary scales, the loops are so small and numerous that spacetime appears smooth, just as a cloth appears smooth to the eye, even though it is woven from threads. But at the Planck scale, the granularity becomes unavoidable. Distances and areas come in quantized units, like pixels on a cosmic screen. In such a universe, the motion of light may be affected by the discreteness of geometry, producing tiny deviations from perfect constancy. Lorentz invariance might hold approximately, but not exactly. If photons sense the loops, their paths may betray it in the faintest measurable ways. Other approaches take different forms. Theories of emergent spacetime suggest that geometry itself arises from deeper principles, perhaps from entanglement in quantum systems, or from holographic descriptions like ADS-CFT. In these frameworks, spacetime is not a stage but a phenomenon, born from the information and correlations between quantum states. Light's constancy may then be a byproduct, an emergent property rather than a fundamental one. If so, it may fail under extreme conditions, offering a new way to test the underlying structure. These theories are diverse, yet they share a common thread. They ask whether the speed of light is truly absolute, or whether it is only absolute within the approximations of our current scale. They challenge Lorentz invariance, either preserving it perfectly as a sacred law or allowing it to bend slightly in the face of quantum gravity. In either case, the implications are vast. If Lorentz invariance is preserved, then light's constancy is elevated to a principle deeper than foam, immune to turbulence, immune to disruption. If it is violated, then photons may carry the message of new physics, betraying the structure of spacetime at its foundation. The question becomes not just scientific, but philosophical. What does it mean for a law to be fundamental? If light's constancy is emergent, then reality itself is layered, with the laws we know built upon deeper, hidden structures. If it is fundamental, then spacetime may be more orderly than quantum mechanics suggests, its foam suppressed by principles we do not yet understand. The answer will determine the shape of physics for the next century, guiding whether we build upon relativity or move beyond it. For now, the evidence favors constancy, but theory insists that the story is not so simple. Somewhere between strings, loops, and emergent geometries lies the truth. Somewhere in the clash between quantum mechanics and relativity lies the explanation for why light behaves as it does, why the vacuum is alive yet so calm, why Wheeler's foam hides so well. To seek this truth is to step into the frontier of quantum gravity, where mathematics stretches imagination and where the fate of Einstein's law will be decided. In the search for a union between relativity and quantum mechanics, string theory and loop quantum gravity are not alone. They are the most famous, but they are joined by other daring approaches, each carrying its own vision of space-time and the speed of light. Some researchers pursue causal dynamical triangulations, a method in which space-time is approximated not as smooth, but as built from tiny building blocks, geometric simplices stitched together like tiles. By assembling vast numbers of these blocks, space-time emerges with properties resembling the continuous geometry of relativity. Yet at the smallest scales, the discreteness might leave traces. If photons sense the lattice, then their motion may betray the granularity, deviating ever so slightly from the perfect constancy predicted by Einstein. Another approach is asymptotic safety, which suggests that gravity becomes well-behaved at extremely high energies due to a hidden fixed point in its equations. If this is correct, space-time does not need to be replaced by new ingredients, but is instead self-consistent across all scales. In such a vision, the foam of Wheeler might be tamed by the mathematics of renormalization, and the speed of light could remain perfectly constant, even at the Planck length. Here, the foam is not absent, but rendered harmless, its chaos cancelled by the deeper logic of the equations. There are also holographic models built upon the bold insight that physics inside a region of space can be fully described by information on its boundary. The ADS-CFT correspondence embodies this idea, proposing that gravity in a curved space is equivalent to a quantum field theory living on its edge. If true, then space-time itself may be no more fundamental than a holographic image, an emergent phenomenon projected from a deeper layer of reality. In such models, the constancy of light is an emergent property of information flow, not a law written into the bedrock of existence. And if emergence can give rise to constancy, it may also allow for subtle deviations under extreme conditions. These diverse theories frame the constancy of light in different ways. Some preserve it perfectly, holding Lorentz invariance as sacred, untouched by quantum fluctuations. Others bend it, predicting violations so faint they escape current experiments. Still others redefine it entirely, claiming constancy as a byproduct of deeper rules. The debate is not merely mathematical, but philosophical. What counts as a law? What counts as fundamental? If constancy is emergent, then it is a surface phenomenon, not the essence of reality. If it is absolute, then our universe is smoother, calmer, and more orderly than quantum uncertainty would suggest. What unites these theories is their demand that we go beyond Wheeler's metaphor and Einstein's equations, into a new territory where geometry, energy, and information intertwine. The speed of light, once thought of as a number carved into nature, becomes a test of theory itself, a probe of whether quantum gravity respects or alters the principles we take for granted. Each framework offers a different answer, and each must be weighed not only by its elegance, but by its confrontation with data. So far, the data favor Einstein. Photons remain constant across billions of years and billions of light years, but theory insists that the story is unfinished. Somewhere in the weave of loops, the vibrations of strings, the tiles of triangulations, or the holograms of information, lies the truth about light and space-time. To uncover it is to step into the frontier where mathematics meets philosophy and where the fate of Einstein's constant will finally be decided. Quantum gravity theories confront us with a choice. Do we cling to the constancy of light as an untouchable principle, or do we accept that it may bend beneath the weight of deeper laws? The answer depends not only on the mathematics, but on the philosophy we adopt about nature. For some, Lorentz invariance must be absolute because its violation would unravel causality, scrambling the order of time itself. For others, the possibility of tiny violations is acceptable, provided they lead to a more unified picture of the cosmos. In either case, the constancy of light becomes the battlefield on which quantum gravity fights its war. Consider again loop quantum gravity. In this framework, space-time is built from discrete chunks, areas and volumes that come in smallest possible units. If photons travel across such a pixelated geometry, their motion may reveal it. High-energy photons, with shorter wavelengths, may interact more strongly with the underlying discreteness, while low-energy photons glide more smoothly. This could lead to tiny energy-dependent delays, just as Wheeler's foam suggested. Experiments with gamma-ray bursts and quasars have already placed strict limits on such effects, but the possibility remains alive, waiting for sharper tools. String theory, in contrast, often preserves Lorentz invariance perfectly. Its mathematics is so rigid that constancy emerges naturally, protected by the symmetries of the strings themselves. But some variants allow for deviations, especially when extra dimensions or exotic branes are involved. In those cases, the speed of light may no longer be a single number, but a property tied to how strings vibrate across hidden spaces. Testing such predictions requires not only astrophysical observations, but also clever experiments at colliders and precision labs, searching for signatures of higher dimensions that might reveal themselves indirectly. Then there are hybrid ideas, where space-time is neither continuous nor strictly discrete, but something in between, a foam that averages to smoothness while retaining turbulence at its core. In such visions, photons may travel unscathed most of the time, but occasionally stumble, producing rare anomalies rather than consistent delays. Detecting such anomalies would require not just timing, but enormous statistical power, analyzing billions of photons across countless cosmic events. Future telescopes and detectors may finally bring such sensitivity within reach. What unites these theories is the recognition that the speed of light is no ordinary constant. It is the linchpin of causality, the cornerstone of relativity, the number that defines how space and time themselves are woven. If it varies, even slightly, the consequences ripple across physics, reshaping our understanding of cosmology, black holes, quantum fields, and the ultimate structure of reality. If it does not vary, then we learn something just as profound, that even at the Planck scale, where uncertainty rules, nature conspires to protect Einstein's law. The outcome of this debate will define the future of physics. If evidence of variation is ever found, we will know that relativity was not the final word, but a glorious approximation, a chapter in a larger story. If no variation is ever found, then relativity will stand taller than ever, its constancy raised from principle to inviolable law. Either way, the hunt for foam and the pursuit of quantum gravity will not end, for the greatest mysteries of space-time are not yet solved. What lies beneath the calm surface of the cosmos remains hidden, but each photon, each theory, each observation brings us closer. And so, Chapter 7 closes on a knife's edge. Quantum gravity offers possibilities as wild as strings vibrating across hidden dimensions, loops weaving geometry from quantum threads, and holograms projecting space-time from deeper realities. Each offers a verdict on the speed of light, whether it is absolute, approximate, or emergent. The next step is to imagine the consequences. If light speed can vary, even by the faintest amount, what would it mean for causality, for relativity, for the future of exploration itself? The thought that the speed of light might not be absolute is more than a technical question. It is a doorway into a universe stranger than anything Einstein imagined. For over a century, the constancy of light has been the foundation of modern physics. Relativity is built upon it. Causality, the order of events in time, depends upon it. The very definition of distance and duration rests on its unchanging pace. To question it is to shake the pillars of reality itself. Yet if Wheeler's foam exists, if quantum gravity bends the laws we hold sacred, then light speed may not be inviolable. And if it can vary, even by the smallest fraction, the consequences ripple through every corner of physics and philosophy. The first and most immediate consequence would be for causality. Einstein's theory ensures that cause precedes effect, that no signal can outrun light to scramble the order of events. If the speed of light can vary, especially if some particles or signals can exceed it, then the boundary between cause and effect becomes uncertain. Information could travel faster than expected, perhaps even backward in time from certain frames of reference. Paradoxes would loom, challenging the coherence of logic itself. Science fiction has long dreamed of faster-than-light travel, but physics has resisted it precisely because of the chaos it would unleash upon causality. If constancy is not absolute, then causality itself may need to be redefined. Another consequence would unfold in cosmology. The early universe presents puzzles that relativity struggles to solve, such as why regions of the cosmos so far apart share the same temperature and density. Inflation theory proposes a period of exponential expansion to explain this, but some physicists have suggested that a varying speed of light could offer an alternative. If light traveled faster in the early universe, distant regions could have communicated and equilibrated before slowing to today's value. This radical idea reshapes the timeline of the cosmos, offering new explanations for old mysteries. Whether correct or not, it shows how deeply our picture of history depends on the constancy of light. There are also implications for dark energy and the fate of the universe. If light speed varies over cosmic time, it may influence how we interpret the acceleration of expansion. Observations of distant supernovae and galaxies rely on light's constancy to measure distances and times. If that constancy shifts, even slightly, our interpretation of the data could change. Dark energy itself might be redefined, perhaps not as a mysterious force, but as a symptom of shifting constants. The structure and destiny of the cosmos may hinge on this subtle question. On a more practical level, a varying speed of light would transform technology. Every device built upon relativity, from GPS satellites to particle accelerators, assumes that light travels at one constant pace in vacuum. If this pace can change under certain conditions, new opportunities and new challenges would arise. Perhaps signals could be tuned to exploit foam, finding channels faster than ordinary light. Perhaps data transfer could break free of today's limits, ushering in technologies that border on science fiction. But the dangers are as great as the promises. If constancy fails, our most reliable technologies might wobble, our synchronization of time might fracture, our grasp on order itself might weaken. Beyond science and technology, there is philosophy. If light's constancy can vary, then what we call laws of nature may not be laws at all, but emergent rules, stable only under certain scales or conditions. This would place the universe closer to a living system than a mechanical one, a cosmos where order arises from chaos rather than being imposed from above. It would mean that even the most sacred of principles are negotiable, that reality is layered, with deeper truths beneath the constants we take for granted. Such a view would transform our understanding of what it means to know, to predict, to explain. The possibilities, both wondrous and unsettling, demand careful thought. Faster-than-light travel might offer visions of interstellar journeys, warp drives, and communication across galaxies. But it might also shatter causality, dissolving the very sequence of cause and effect that makes science possible. Cosmological puzzles might be solved not by inflation or dark energy, but by a subtle shift in light speed. But such solutions would demand a radical rewriting of physics. Technology might leap into realms undreamed, but also falter if constancy proves unreliable. At every turn, the question pushes us beyond comfort into the unknown. And yet, for all these possibilities, the evidence remains firm. Photons refuse to stumble. Light holds steady across billions of years. Relativity's constancy remains unbroken. If variation exists, it is faint beyond our reach, perhaps a ghost of a whisper hidden in the foam. But the thought alone is enough to stretch our imagination. to remind us that even the most trusted laws may conceal deeper mysteries. The story of a varying speed of light is not only about physics, it is about the limits of knowledge, the fragility of certainty, and the courage to ask whether the unbreakable can be broken. If the speed of light can vary, then relativity itself would need to be reinterpreted. Einstein's framework rests on the principle that all observers, no matter their motion, measure the same pace of light in vacuum. This is what fuses space and time into spacetime, what ensures that the laws of physics are the same for all. If light speed shifts under certain conditions, then the very scaffolding of relativity trembles. Perhaps the theory would not collapse entirely, but it would need modification, an expansion that admits variability where once there was constancy. The consequences of such a revision would be profound, rewriting textbooks and reshaping our understanding of the cosmos. One of the most startling consequences would be for information transfer. In our universe, information is limited by light's constant pace. This limit preserves causality, ensuring that no message outruns the boundary between past and future. But if that pace varies, then the barriers may bend. Information might leak faster than light, slipping between regions once thought forever separated. In principle, this opens the door to warp drives and wormholes, science fiction technologies long dismissed as fantasy. If space-time itself can flex in such ways, perhaps propulsion through foam or shortcuts across geometry could become possible. The dream of crossing interstellar distances in human timescales might rest not in brute force engines, but in the subtle variability of light. At the same time, such possibilities invite dangers. Faster than light communication or travel threatens to unravel causality. Imagine sending a signal that arrives before it was sent, a paradox that destabilizes logic itself. Entire frameworks of physics are built to prevent such contradictions. If light's constancy wavers, then either paradoxes must be accepted, or new principles must emerge to protect order. Perhaps variability exists, but always within boundaries that preserve causality, a delicate balance between freedom and stability. Or perhaps our understanding of causality itself must evolve, expanding to account for phenomena we have yet to witness. Cosmology, too, would be transformed. If light speed was greater in the early universe, then horizons that seem disconnected today could have shared information long ago. The uniformity of the cosmic microwave background, one of the great puzzles of cosmology, might be explained not by inflation, but by a variable speed of light. This would offer an alternative vision of the early universe, one where the laws themselves shifted as conditions changed. The cosmos would not be a stage of fixed rules, but a system evolving in both content and law. Such a vision is radical, but it has been seriously proposed by physicists who see in it a way to solve puzzles inflation leaves unanswered. Even the mysteries of dark energy and dark matter might be recast in this light. If the pace of photons changes across cosmic time, then our interpretation of redshifts, distances, and expansion rates would shift with it. What we attribute to dark energy might partly be the symptom of assuming constancy where there is variation. Similarly, the apparent effects of dark matter on galactic scales might be influenced by subtleties in how light propagates through space-time. These are speculative ideas, but they show how deeply our understanding of the universe rests on the assumption of light's unwavering pace. Change that assumption, and the universe itself must be reinterpreted. On the scale of human life, the implications remain no less dramatic. Every technology that relies on relativity assumes constancy, from satellite navigation to synchronized communication systems. If variation were discovered, even at a subtle level, our instruments would need recalibration. But beyond correction lies opportunity. Perhaps communication could be made faster than thought possible. Perhaps computation could tap into space-time itself. Perhaps new industries could emerge from harnessing variability. The line between physics and engineering blurs when laws once considered absolute become tools to be shaped. Still, these dreams and fears remain speculative. The evidence so far gives no sign of variability. Every photon, whether from pulsars, quasars, or gamma-ray bursts, keeps faith with Einstein's principle. But the imagination cannot let go of the possibility. If variability exists, it would mean that our universe is not a rigid system of fixed laws, but a dynamic entity, alive in ways we are only beginning to glimpse. Constancy would then be not a law, but a shadow, a reflection of deeper, shifting rules. The idea stretches not only science but philosophy. Are the laws of nature eternal truths, written into the cosmos once and forever? Or are they emergent patterns, arising from deeper chaos, stable only across certain scales? If light speed can vary, then the latter vision gains strength. The universe becomes less like a machine and more like a living system, where rules adapt, evolve, and emerge from hidden layers. To discover variability would not only change physics, it would change our conception of reality itself. If the speed of light can vary, then every corner of physics must be revisited. Our measurements of the cosmos, our definitions of distance and time, even the structure of reality as we describe it, all rest on Einstein's constant. To question it is to loosen the very bolts that hold the universe together in our minds. Yet such questioning is not reckless. It is the natural next step in the pursuit of truth. If constancy is absolute, the tests will confirm it again and again. If it falters, even slightly, the cracks will show. One of the greatest consequences of variability would be for black holes. These objects are already paradoxes, where relativity predicts horizons from which nothing, not even light, can escape. If the speed of light changes under extreme conditions, perhaps horizons are not so absolute. Perhaps photons near the edge of a black hole might move differently than we expect, leaking signals where none should exist. This could alter our picture of evaporation, of Hawking radiation, even of the ultimate fate of information in the universe. A varying light speed could mean that black holes are not prisons, but laboratories, testing grounds where the laws we thought unbreakable reveal their deeper nature. The same logic applies to wormholes and warp drives. In standard relativity, they remain exotic possibilities, constrained by negative energy or unattainable conditions. But if constancy itself bends, perhaps these routes are not as impossible as we think. A frothing space-time might open and close pathways in ways that photons could exploit, allowing shortcuts through the vacuum. Travel across the stars might then be less about brute force and more about learning how to ride the turbulence of space-time. The dream of crossing the galaxy could rest not in breaking Einstein's law, but in discovering where it bends. Cosmology would also shift in profound ways. A universe where light speed changes over time is not static in its rules. Its history is written not only in matter and energy, but in shifting laws. Perhaps the first few seconds after the Big Bang were governed by a faster light, allowing the cosmos to achieve the uniformity we observe. Perhaps the acceleration we attribute to dark energy is not driven by a new force, but by the slow drift of light, speed across billions of years. In such a universe, the constants are not constants at all, but evolving parameters, and cosmology becomes the study not only of matter and space, but of laws themselves. For human thought, the implications are staggering. We have always sought constants as anchors in a changing world. The constancy of light has been such an anchor, a truth that seemed eternal, a foundation upon which relativity, cosmology, and technology were built. If even this can vary, then certainty itself becomes fragile. The laws of physics become stories told by nature under certain conditions, stories that may shift as the setting changes. To embrace this vision is to accept a cosmos less like a clock and more like a living ocean, where order emerges from turbulence and stability from fluctuation. And yet, evidence is stubborn. Every photon tested so far keeps pace with Einstein's law. No deviation, no delay, no fracture has revealed itself. The constancy of light seems as solid as ever, immune even to the vast journeys across cosmic time. Perhaps it will never break, Perhaps relativity is not an approximation, but a final truth. Or perhaps we stand on the edge of discovery, with variations too subtle for our current instruments, waiting for the next leap in precision. Either way, the search itself is transformative. It forces us to ask what it means for a law to be fundamental, what it means for certainty to exist, what it means for reality to reveal itself. If light speed can vary, then relativity is not the end of the story, but a chapter. If it cannot, then relativity is raised to the level of eternal law. In either case, the search guides us forward. It stretches our imagination, sharpens our tools, and forces us to confront the deepest layers of reality. The possibility of variability is not just a question about photons, it is a question about truth itself. The closer we approach the Planck scale, the more the universe resists us. Our instruments falter, our theories strain, and our imagination alone dares to cross where experiments cannot yet follow. The Planck length, about 10 to the power of minus 35 meters, is so small that it makes the width of a proton seem like a continent compared to a grain of sand. At such scales, Wheeler's foam is expected to roil, where space-time bubbles with wormholes, fluctuations, and turbulence beyond our comprehension. But to see it directly would require energies far beyond anything humanity can generate, far beyond the reach of our most ambitious machines. Particle accelerators, the proudest tools of modern physics, can smash protons together at energies of trillions of electron volts. These collisions probe the structure of quarks and gluons, mapping the innermost workings of matter. Yet even at these extremes, we are still 20 orders of magnitude below the Planck energy required to probe space-time itself. The gap is so vast that it seems insurmountable. To build a machine capable of directly reaching the Planck scale would require a collider the size of a galaxy, a project beyond even the dreams of science fiction. And so physicists must turn to cleverness rather than brute force. If we cannot create the conditions of the Planck scale, we must search for their echoes. Photons traveling across billions of light years become our messengers, as we have seen in gamma-ray bursts, quasars, and pulsars. Gravitational waves, ripples in space-time itself, may also carry imprints of the foam, subtle distortions that accumulate as they pass through the frothing vacuum. Quantum sensors, instruments designed to measure with sensitivity at the edge of uncertainty, may one day detect fluctuations in the vacuum fields themselves. Each of these methods is indirect, but each holds the promise of bringing the foam into reach without colliding galaxies to do so. The difficulty is that the signals are faint, buried in noise. A single fluctuation at the Planck scale is unimaginably small, drowned out by countless larger effects. To see it, physicists must gather vast numbers of events, searching for statistical patterns that betray the hidden turbulence. This is why observations of cosmic light are so valuable. Billions of photons traveling across billions of years amplify the effects, giving us the chance to hear whispers that would otherwise be lost. Even then, the task is daunting. Separating foam from astrophysical noise is like listening for the flutter of a butterfly in the middle of a hurricane. Yet humanity persists. Instruments grow more sensitive year by year. Interferometers that detect gravitational waves can now measure displacements smaller than a proton's width. Atomic clocks can keep time so precisely that they lose less than a second over the entire age of the universe. Quantum entanglement allows measurements that surpass classical limits, squeezing uncertainty to reveal what was once hidden. These technologies are still young, but they point toward a future where probing the foam may no longer be fantasy. The edge of measurement is not fixed. It is a frontier we push forward, one breakthrough at a time. The challenge is not only technological, but conceptual. Even if we reach the sensitivity required, what exactly should we expect to see? Foam is not a single prediction, but a metaphor, a vision of turbulence at the foundations of geometry. Different theories of quantum gravity paint different pictures. In some, foam blurs light's path, delaying photons of high energy. In others, foam is cancelled by symmetries, leaving photons untouched but influencing gravity instead. In still others, foam manifests only statistically, visible only in subtle deviations across enormous datasets. Our instruments may soon reach the edge of measurement, but without clear guidance, we may not know what we are looking for. At the edge of measurement, physics becomes as much philosophy as experiment. We are forced to ask whether reality is knowable at all scales, or whether some layers are forever beyond reach. Perhaps space-time foam exists, but its influence is always cancelled, always hidden, leaving no trace. If so, then we face a limit not of technology, but of principle, a horizon of knowledge beyond which we cannot pass. Or perhaps the foam does leave traces, faint but real, waiting for us to sharpen our tools enough to find them. The question lingers like a challenge, daring us to push farther. The search for foam is not just about physics. It is about the human drive to know, to push against the limits of measurement, to peer into the smallest and largest scales. Even if we never touch the Planck length directly, the effort reshapes our imagination, expands our technology, and forces us to rethink what it means to measure, to know, to understand. At the edge of measurement, we discover not only the structure of the universe, but the nature of our own curiosity. At the edge of measurement, every improvement in technology becomes a leap toward the unknown. When Galileo first lifted his telescope to the sky, he expanded human sight by only a few orders of magnitude, yet revealed moons circling Jupiter and mountains on the moon. Today, physicists aim to expand sensitivity by dozens of orders, enough to glimpse disturbances at scales once thought untouchable. The ambition is staggering, but so is the payoff. To capture even a faint echo of foam would be to witness the first direct sign of quantum gravity, a discovery as revolutionary as relativity or quantum mechanics themselves. One promising path lies in gravitational wave astronomy. Ripples in space-time travel across the universe, carrying information about colliding black holes, merging neutron stars, and perhaps even events from the earliest moments after the Big Bang. Detectors like LIGO and Virgo can already sense distortions smaller than a proton across kilometers of vacuum tunnels. But what if these ripples also carried imprints of foam? As they cross billions of light years, the fluctuations of space-time might scatter them, adding faint noise or altering their coherence. If detected, this noise could reveal the underlying texture of geometry itself. Already, researchers are combing gravitational wave data for such signatures, though none have yet emerged. Another path is through quantum sensors. Atomic clocks have reached extraordinary precision, able to detect changes in gravitational potential from moving a device a single centimeter higher on Earth's surface. Arrays of such clocks may one day measure fluctuations in space-time at levels far beyond today's reach. Interferometers using entangled particles can surpass classical noise limits, offering glimpses into variations too subtle for ordinary instruments. These technologies are still young, but they hint at a future where the foam might be mapped, not as a metaphor, but as a measurable phenomenon. There is also the possibility of cosmic relics. The early universe was a crucible of unimaginable energy, far closer to the Planck scale than anything we can create. If foam existed then, it may have left traces in the cosmic microwave background, the faint afterglow of the Big Bang. Patterns of polarization, small deviations in temperature, or unexplained correlations might all carry the imprint of frothing geometry. Future missions, more sensitive than Planck or WMAP, may be able to search for these fingerprints with unprecedented clarity. The past may hold the key to the scales we cannot touch directly. The edge of measurement is not only about instruments, but about courage. It requires us to imagine possibilities that may never be confirmed, to invest decades in building devices that may yield silence, and to confront the limits of human reach. Yet history shows that silence is not failure. The absence of evidence for foam so far has already reshaped theory, forcing models to become subtler, more precise, more disciplined. Each null result trims the wild branches of speculation, guiding us closer to whatever truth lies hidden. In this sense, even the void of evidence becomes a teacher. But there remains a haunting possibility, one that scientists whisper about with both humility and awe. What if the foam is real, but forever beyond detection? What if nature has hidden it behind a wall that no technology can breach, no matter how refined? In such a universe, the deepest truths may exist without ever becoming knowable. Knowledge would then have boundaries not imposed by our imagination, but by reality itself. To accept this would be to accept a limit not of tools, but of principle, a horizon beyond which curiosity can never pass. And yet, humanity has never been content with limits. From the discovery of atoms to the detection of gravitational waves, we have again and again reached beyond what was thought possible. The edge of measurement is not fixed. It shifts with every innovation, every breakthrough, every leap of imagination. To stand at this edge is to glimpse the boundary between the known and the unknowable, and to step forward anyway. Even if the foam forever evades us, the pursuit itself transforms us, driving progress in technology, sharpening our questions, and reminding us that the cosmos is greater than our grasp. At the frontier of measurement, physics and philosophy blur together. The Planck scale is not merely small, it is almost unspeakably so. A gulf between what we can reach and what we long to know. To imagine probing, it is like imagining touching the horizon, always out of reach no matter how far we walk. Yet this impossibility does not stop us. It fuels us. Every new technology, every new theory, is an attempt to shorten the distance between imagination and reality. Physicists know that even null results carry meaning. The absence of observed foam in the timing of photons or the clarity of distant galaxies narrows the space of possibilities. It tells us that if foam exists, it must be weaker, subtler, or differently structured than once believed. Each non-detection is a clue, shaping the evolution of theory. In this sense, the silence of the universe is not empty. It is filled with information, guiding us like the faint stars that mark the edges of the night. Still, the temptation is strong to believe that with enough ingenuity, we will one day hear the foam directly. Perhaps the next generation of telescopes will capture photons with precision fine enough to betray tiny jitters. Perhaps gravitational wave detectors will evolve into quantum observatories, mapping the froth as ripples of geometry itself. Perhaps quantum computers, with their unparalleled sensitivity to entanglement and coherence, will become tools for probing space-time at scales no classical device could reach. These dreams may sound distant, but so did the detection of black holes or the mapping of the cosmic microwave background. Progress often comes not as thunder, but as a quiet step into the unknown. And yet, even if detection never comes, the pursuit matters. At the edge of measurement, we confront our own limitations and learn to stretch them. We develop instruments that sharpen medicine, improve communications, and extend human reach in ways unimagined when the quest began. The technologies born from chasing foam may transform the world even if the foam itself remains forever hidden. This is the paradox of science at the edge. Even when we fail to find what we seek, we succeed in reshaping ourselves. There is also humility here, a reminder that the universe is not obliged to reveal its secrets. Perhaps there are layers of reality forever beyond us, mysteries we can approach but never touch. To live with that possibility is not defeat, but maturity. It means accepting that knowledge has horizons, and that meaning lies not only in answers, but in the questions themselves. Wheeler's foam may remain a metaphor, or it may one day be confirmed as the texture of space-time. Either way, it has already changed how we think, how we measure, and how we dream. The chapter closes with a vision of humanity standing at the edge of measurement, peering into the abyss where certainty falters and imagination begins. We do not yet know whether foam is real, whether light stumbles in its journey, whether space-time is smooth or turbulent. But we know that asking these questions has drawn us closer to the essence of reality than ever before. The next step may belong to instruments not yet built, to theories not yet written, or to generations not yet born. For now, we remain at the edge, listening for whispers in the silence, waiting to hear whether the foam of space-time will ever speak. The story of light, foam, and the search for quantum gravity has carried us across a century of discovery, speculation, and silence. We began with Einstein, who showed us that the speed of light is not just a number, but the backbone of reality itself. We followed into the strange depths of quantum mechanics, where the vacuum seethes with restless energy. We imagined Wheeler's vision of space-time foam, a universe whose foundation bubbles like an ocean in storm. We tested that vision with photons from gamma-ray bursts, with quasars and pulsars, with galaxies at the edge of time. Again and again, the cosmos answered with constancy. Light refused to falter. And yet, the mystery endures. If space-time foams, it hides its turbulence too deeply for us to see. If light can vary, it does so with such subtlety that even billions of years of travel leave no scar. The silence is eloquent. It tells us that our theories are incomplete, that reality may be smoother or stranger than Wheeler's metaphor suggests. But it also tells us something more profound, that the act of searching, of questioning, of pressing against the limits of knowledge, is itself part of what it means to be human. Light remains constant in our experiments, and yet it is never ordinary. It guides us across the universe, from the birth of stars to the death of galaxies. It reveals the geometry of space and the expansion of time. It carries within it both the proof of relativity and the challenge of foam. Each photon is a paradox, at once particle and wave, messenger and mystery. Whether it stumbles or not, it forces us to ask deeper questions about reality itself. The constancy of light may be a law, or it may be an illusion born from scales larger than the Planck length. Either way, it has become more than a number. It has become a symbol of our relationship with the universe. We build our theories upon it, but we also test those theories against it. We trust it, but we also question it. In that tension lies the heart of science, the balance between certainty and doubt, between law and imagination. If the foam is real, one day we may find its traces. Perhaps a new telescope, a new detector, a new theory will reveal the hidden turbulence. If the foam is not real, then we will have learned something equally profound, that relativity is not only an approximation, but a final truth, a law written into the very essence of reality. Either outcome expands our vision, guiding us closer to the edge of knowledge. And so, as this story closes, we are left not with answers but with wonder. Light may be constant, or it may stumble through the froth of space-time. Foam may be the true texture of reality, or it may be a metaphor pointing to something even stranger. We do not yet know, but we know that asking the question has expanded our imagination, sharpened our tools, and deepened our sense of place in the cosmos. The mystery itself is constant, and in that constancy lies the beauty of science. At the end of our journey, we find ourselves circling back to where we began, to Einstein's simple but radical declaration that the speed of light is constant in a vacuum. That principle has endured every test we have devised, from laboratory experiments to cosmic observations. It has survived the scrutiny of telescopes peering into the hearts of quasars, satellites recording gamma-ray bursts, and detectors listening to pulsars ticking like celestial clocks. Each time, the result has been the same. Light holds steady, refusing to betray even the faintest stumble. Yet physics thrives not only on confirmation, but on doubt. The very act of questioning whether light speed can vary has reshaped the landscape of science. It has inspired the development of theories like string theory and loop quantum gravity, frameworks that seek to reconcile relativity with quantum mechanics. It has pushed engineers to build instruments of astonishing precision, capable of measuring displacements smaller than a proton and timing events across billions of years. It has forced us to grapple with the possibility that the laws of nature may not be absolute but emergent, born of deeper structures we cannot yet see. This tension between constancy and possibility defines the constancy of mystery. We trust the laws that guide our science, but we also challenge them, because history has shown that no law is safe from revision. Newton's mechanics reigned for centuries until relativity and quantum mechanics revealed its limits. Relativity may reign today, but if foam is ever confirmed, it will be revealed as an approximation, a chapter rather than the whole story. To doubt is not to weaken science, it is to keep it alive. And what of us, the searchers? We stand on a small planet orbiting an ordinary star, yet we dare to ask whether the very fabric of space-time foams at scales 1 trillion times smaller than a proton. We dare to build machines that listen for whispers from black holes and photons that began their journey billions of years ago. We dare to confront questions that may never be answered, because the pursuit itself is its own reward. In searching for foam, we discover not only the structure of the universe, but the scope of our own curiosity. If the answer comes tomorrow, or in 1,000 years, it will not end the mystery. Each discovery opens new questions. Each explanation leads to deeper puzzles. If light is constant, why is it so? If foam exists, what principle hides it from our view? If laws are emergent, what deeper structures give rise to them? The mystery is not diminished by answers. It is amplified, spiraling outward like the universe itself. Perhaps this is the greatest lesson of all. The constancy of light is matched only by the constancy of mystery. The universe gives us enough clarity to guide us, enough consistency to build knowledge, but always leaves a horizon of unknowns, a frontier that beckons us forward. To live in such a universe is to live in wonder, suspended between what we know and what we dream. And so we continue, guided by photons, haunted by foam, carried ever forward by the constancy of mystery itself. Light, foam, constancy, and doubt. These are the threads that have woven our journey, and as we arrive at its end, the tapestry remains unfinished, deliberately so. For the universe does not give us closure. It gives us glimpses, fragments, questions that linger at the edge of thought. We began with Einstein's speed limit, precise to the last meter per second, a law so elegant it reshaped space and time. We descended into the vacuum, discovering it alive with quantum fluctuations, restless even in emptiness. We followed Wheeler into his vision of space-time foam, a frothing geometry at scales too small to picture. We searched the sky for signs, bursts, quasars, pulsars, galaxies, and found light unwavering, constant in its defiance. We turned to theories of quantum gravity, to strings, loops, and holograms, each offering a different verdict on constancy. We imagined the consequences if light could vary, for causality, for cosmology, for the future of exploration. And finally, we arrived here, at the edge of measurement, where science meets philosophy, and the only certainty is mystery. In this final reflection, what strikes most is not what we have learned, but how we have learned. We build machines to measure whispers, telescopes to catch photons born before Earth itself, equations to model realities no one has ever seen. We ask questions so vast that they humble us, and yet we keep asking. This persistence, this refusal to stop, is perhaps the most constant thing of all. The cosmos may or may not foam, light may or may not falter, but human curiosity endures. It is our own speed limit, the pace at which imagination outruns certainty, always pushing forward. The closing vision is cinematic. Imagine the universe as an ocean, dark and endless, its surface calm under starlight. We sail upon it with fragile ships of theory and instrument, our compasses built of photons, our maps drawn from the patterns of galaxies. Beneath the surface, Wheeler tells us, the water churns with foam. Einstein tells us it is smooth. The stars above keep shining, indifferent to our debate. And yet, we continue to sail, not because we expect to master the ocean, but because the act of sailing is what makes us human. Light may be constant, or it may stumble through the froth of space-time. Either way, it carries us. It carries us across billions of years, across the gulf between stars, across the gulf between certainty and doubt. It illuminates not only the cosmos, but our own minds, showing us that knowledge is never finished, that mystery is never banished. In the constancy of light and in the constancy of mystery, we find the same truth. The journey matters more than the destination. The search is infinite, and in that infinity lies our meaning.